Hi, my name's Rick. I actually am just now meeting Timo, but everyone else here I've talked to about proof of stake at least a little bit. The idea behind this panel is we're all going to basically communicate the sort of the similarities. We're going to give a brief description of each system. I have a timer. I'm going to try to keep it to 5 minutes per system. And we'll be discussing, primarily, like I said, what the similarities between these systems are. And then we'll have a discussion about some of their differences. Maybe we'll open it up to questions, which will be interesting. Some of those questions will need to be carefully directed, and we'll try to make sure that all happens in time. I think I'm just going to say, well, I'll let each team talk about their product and themselves a little in 5 minutes, and we'll start with who should we start with? Let's start with Jay.
So it's total 5 minutes, not 5 minutes per person. Is that right?
Oh. Yeah, it's no. I think it's 5 minutes per team. There's one team that's stacked the deck a little, so they don't get 10 minutes.
Okay, great. So, my name is Jay Kwan, and I'm here representing Tendermint, which is a Byzantine fault-tolerant blockchain engine. It's an open source engine that we've been developing since 2014, and now it's pretty solid and almost production ready. So that Tendermint is one project. The other thing I'm representing is Cosmos. And Cosmos is a network of proof-of-stake blockchains, not just public blockchains, but also private chains as well. And at the heart of Cosmos is the Cosmos Hub, which is a Tendermint-powered proof-of-stake blockchain. So I got into this space early on in 2014 when I was trying to search for a solution for an alternative to proof of work. And I found a solution just by rummaging through old academic papers about Byzantine fault-tolerant algorithms, and have been iterating upon that to create a middleware, an engine that can be used to create any blockchain application. So I can talk more about Tendermint later, but it's there. We created Tendermint because we want people to use it. So if you want to create a new blockchain, consider building on Tendermint. We've made it easy to develop any blockchain written in any language. So check it out.
All right, thanks, Jay. I think next we'll probably do Peter from Parity.
Hi, everyone. I'm Peter from Parity, as Rick said. We make the Parity implementation of Ethereum, and as we've been developing it, of course, the first consensus engine that is available is the proof of work consensus engine that is used now by the Ethereum network. Because it's implemented in a way that provides a fairly clear division between the consensus mechanism and the state machine, we are now able to introduce different consensus algorithms. And basically we first of all try to make it easy to implement different consensus algorithms by figuring out what are good abstractions in which we can talk about different consensus algorithms and how they are in a way similar to each other. So I think at some point we'll be very keen to implement all the consensus that is being talked about here. But what we started with were some so-called proof of authority type of consensus algorithms. So basically that means that there is a pre-specified list of validators that between which the consensus is achieved. So One example of that is a simple round-robin type consensus. Another is Tendermint, which we recently implemented. But there will be also another implementation that we are working on based on a published BFT variant called Ziziva. We'll call it ABAP probably for now, which will be a blockchain alternative to that, which performs hopefully better in an optimistic case. So when the leader or a primary is non-faulty, which would lead to maybe less messages exchanged than in a case of Tendermint. But that only provides a consensus amongst this set of fixed validators or authorities. What we really want is proof of stake. So the simplest way to introduce proof of stake is to add a stateful validator set that depends on the stake. So in a case of Ethereum virtual machine, the state can be modified by the contracts, and basically we have a staking contract that right now one implementation includes nomination or delegated proof of stake, which can be tied with any of the consensus algorithms such as Ethereum or ABAP. And then we have for each of the faults in a Byzantine sense, for instance, we can report back to the staking contract to do slashing or remove the stake in some other way, or remove the validator from the validator list. Hopefully we can also extend those abstractions to also work with a consensus where actually the events during the consensus process affect the validator set as well. So yeah, in general, we have parity right now with you can configure it to run with different consensus algorithms, and then those consensus algorithms can make use of different validator sets, which can be specified using contracts, in this case, staking contract. So that's the basic approach.
Thanks, Peter. And then Dominic, I guess you're going to go. Try to keep it around 2.5.
Okay. So I'm here representing Dfinity. Dfinity is conceived as a kind of experimental Ethereum sister network. It involves two main axes of work. One is in relation to novel cryptography and network protocols that can increase the performance of networks, specifically kind of proof-of-stake networks, although there's a computational element to some of the stuff we do. Tomorrow I'll probably present this thing called threshold relay, which is a technique that uses unique deterministic threshold signatures to produce finality in public blockchains much more quickly. So we believe we can bring down finality on a public network with even millions of nodes to a few seconds. So we're providing performance similar to what people expect on a private network on a public network. So that's one axis of work, and also other protocols related to scaling the computational capacity. Much of this might make its way into Ethereum, hopefully. If it could be reused, it'd be fantastic. And then the other axis is introducing this idea of a distributed, omnipotent distributed intelligence that can control economic parameters, upgrade the protocol, freeze contracts, run arbitrary code using privileged EVM instructions. It's called the blockchain nervous system. And it changes the traditional blockchain paradigm of the code is law to one where is the AI is law. And obviously it's quite experimental. It'll be very interesting to see what happens. And so yeah, that's it. Those are the two main elements. New crypto that improves the performance and scalability of Ethereum-style networks, and this distributed intelligence called blockchain nervous system.
Thanks. Timo?
Yeah, so I'm working on the Dfinity project as well that Dominic has introduced, and yeah, we have some very interesting, exciting ways to think about proof of stake, I think. Maybe we can just give one or two ideas that can later be picked up in the discussion. So for instance, we heard in the morning in the talks from Vitalik and Vlad that proof of stake can actually be more secure than proof of work, and the reason is that the miners or mining identities can actually be punished, and not only their reward can be taken away. And that has the potential to make it more secure. But if we look at it closely, what does actually allow us to punish the miners is not really the proof of stake, but it's the fact that there are identities that are somewhat permanent or existent over a period of time. And so the way that we like to think about it is to disentangle the two things, the existence of a miner identity and the consensus protocol itself. So we use the proof of stake to create mining identities in some way, and then on the basis of existing mining identities, we build a consensus algorithm. And for that part, it doesn't really matter how the identities are created as long as they are Silber resistant. So we like to think about this entanglement. Yeah, just one point for the discussion.
Yeah, thank you. Those are interesting ideas. And then, Vlad, I think you should probably be next.
Hi. Yeah. So I've been working on proof of stake basically, especially ever since I got into security deposit-based proof of stake. I started working on it when Vitalik introduced me to Slasher, and then when I kind of like realized the security deposits like provided Slasher a lot of leverage, I became quite passionate about it. My focus has always been kind of on economic security, and it started off with like just kind of independent choice like game theory, and then moving to the bribing attacker, and then the kind of coordinated choice game theory with like the cartel model. You know, kind of very much along the lines of Vitalik's presentation this morning. And so I see most of this, I see most of the blockchain space, like most of the proof of stake space, through that lens of like the kind of oligopolistic model that I assume, where there's like concentration of power and coordination between the powerful entities. And my concern is that like, you know, if we're not careful, we will let like the whales run crypto. And you know, I think like that's one of the big purposes of proof of stake, as far as I'm concerned, is to shackle coin holders and to like stop them from actually taking control of the protocol.
Thanks, Vlad. And then Vitalik to round it out.
Yeah. So I've been studying proof of stake as well for the past 3 years or so. I originally published that Slasher post back in January 2014, and at the time, we were just thinking kind of very naively about, you know, just realizing that you have this idea that if you can use penalties as well as rewards, then you can solve the nothing at stake problem in proof of stake algorithms. But since then, we've ended up spending quite a lot of time thinking, going through and various different kinds of ideas, including just like one-round consensus, consensus by bet, punishing being incorrectness versus punishing availability, incorporating traditional BFT algorithms, chain-based algorithms, synchrony models. So I've been spending 3 years on kind of building up various different concepts, trying various different approaches, making and testing some proof of concepts for various different approaches, figuring out what the limits are. And personally, I'm actually interested in proof of stake for 2 reasons. So one of them is that and this is true both with existing proof of stake and with you know, kind of much older algorithms, like even the ones that are vulnerable to all these nothing at stake issues, which is it has much lower energy consumption than proof of work. And this has both a kind of social benefit, which is that, you know, you spend less resources, you don't kill trees as much, and this also turns into a private benefit for coin holders, which is that you have less inflation. So that's one reason. Now the second reason is one that really starts to shine if you start moving into the proof of stake protocols of the kind that myself and Vlad have been working on maybe just for the past 6 to 12 months or so, is that the cost, first of all, the cost of taking the system down becomes much, much higher. And second of all, the ability to recover from attacks is much easier. Right. So, for example, in proof of work, there's something that I call the spawn camping attack, which is where if you have enough hardware to 51% attack a chain, then you could just 51% attack it over and over again. And okay, fine, you can hard fork to a different kind of proof of work, but then if you have twice as much hardware, then you can spawn camp the new chain, and you can't hard fork twice because the second time around you're already using general purpose hardware, which basically means that people can kill Bitcoin as it stands entirely for a budget of maybe $500 million, and Ethereum for like maybe 5 to 10 times less that, right? So with proof of stake, on the other hand, if, sure, you can buy up a huge pile of Ether, and sure, you can 51% attack the chain, but then basically all you need to kind of recover from that fault is basically a community kind of run hard fork, right? So basically a similar situation to, let's say, the Geth parity consensus failure we had last year in November. Sure, the community loses a day, maybe you lose 2 days, but you can get back on your feet. And if they want to knock down the chain again, okay, great, they can knock down the chain again, burn another $90 million, and you have another hard fork. And, basically because it's so expensive to do each one of these attacks, in theory, like the attacker should basically eventually even give up. And, you have a second factor, which is that potentially these attacks might even make the price of the underlying cryptocurrency token go up every time they're happening because the attacker is continually deleting their own money. So that kind of asymmetry is something that really attracts me. And right now, my research is around thinking about how to design kind of very minimal proof of stake protocols that add the kind of safety guarantees that we want to have and make it kind of as simple as possible, and try and kind of come up with the simplest possible thing that can be safely and fairly quickly implemented into Ethereum, and then kind of go from there and make the properties more and more optimal over time.
Thank you, Vitalik. So I have some questions for the panel, and I'm trying to figure out exactly which questions I think are best. Everyone on the panel, I think maybe not parity, but everyone else discussed operating a public network. And so I would like to discuss, I would like everyone to sort of chime in on do you believe that, well, I think everyone sort of touched on this point, but maybe didn't state it explicitly. What are the risks to running proof of stake in public compared to running proof of work? We've had some and then I have some follow-up questions for that after.